So, welcome to the last lecture of this class. So, as you can see from this title screen, and today what we actually want to do, we want to do a little bit of recap what we learned in general, but also what I would like to do, there are some questions inside on these slides, and I would like to ask you to help with answering these questions, because that's something that we can see in exam. So that's a question, approximately the type of questions you will be asked, and you need to have the understanding. So in order to prepare you a little bit, I had these questions here. So first of all, it was actually surprisingly good in relation to the syllabus that we planned. So to be honest, the first 6 weeks were exactly on time, were exactly what we wanted. We discussed the foundations of machine learning. We discussed a little bit of deep neural networks. Then we discussed important features of the networks, like loss functions. We discussed a bit backpropagation without going too deep into mathematics. So it was really surprisingly good in time. Then we discussed deep neural networks and training evaluations, convolutional neural networks, 2 lessons for them. Week 7 was the same, transfer learning, few-shot learning. Then we spoke about generative neural networks. I'm not sure if in the same order or not as planned. What changed quite a lot, what changed week 9, 10, 11, because they are quite mathematically heavy, we decided, okay, we will talk a little bit more about generative neural network. We expanded this a little bit to include diffusion, state-of-the-art problems. We decided to abandon Bayesian machine learning because it's really very probabilistic heavy. And instead of that, we talked about recurrent neural networks. And finally, we talked about not active learning in this case, but reinforcement learning, which is somehow close. And finally, we didn't talk about physics-informed neural networks. There is 3 weeks ago, the ETH Zurich released on YouTube a whole class on the physics-informed neural networks, and I will send you a link into the Ilias. Just if you're interested in that, go there, but beware, it's really mathematically heavy. So yeah, and then the last week, it's recap. That what we are doing right now. I think it went very, very good from the point of view of the material. So, and again, when we do recap, we always refer to the first lecture. And on the first lecture, if you remember, I introduced this sort of 3 different topics: artificial intelligence and this umbrella term under which you will find machine learning and deep learning. And I'm quite happy that actually you probably right now recognize all these terms from the deep learning. We know convolutional neural networks. We know MLP, it's a multi-level perceptron, just now a deep, fully connected layer. We have GANs, we have variational autoencoder, RNNs, and transformers. We even were able actually to capture a little bit from here. We talked a little bit about support vector machine, so that's also quite good. So returning back to the hype cycle, in order to, right now, with your new knowledge, to put this research and this thing that we discussed during this class into the hype map. It's, again, this quite recent, so from last year, therefore it's quite accurate. So what we discussed, the deep learning right now, it's already kind of very mature topic in general. So, but what we discussed as well, we discussed the generative AI. We even didn't reach peak yet. So this is one of the hottest topic right now. We talked a little bit about what do we have else here? Kind of natural language processing. It's not what we discussed in transformers in RNNs, but I think we should have something like that here. It's interesting why we don't have, but it should be somewhere here. All these things related to the ChatGPT and other stuff. So for some reason they are not here. But what we also briefly discussed, the computer vision actually. So we used YOLO, it's a method from deep learning, but with application to a very, very well established and mature field of computer vision. So we are quite good with that. And another slide from the past, you remember this one. So when we have output, we have input, and they are somehow connected. What we can look for 2 different things. We can look for a Y, and in this case, we're doing the simulation, predictions, and classification. And this is a sort of the the main part of our course, because it's basic. Then we had chance to look at the optimization and generation. So we looked at the GANs and we looked at the variation autoencoder and even on these diffusion models. And finally, we didn't had a chance to learn physics, but it's really, again, according to the scheme, it's much harder. So and now what I would like to go through lecture by lecture and just maybe recall a very important aspects there and just refresh your memory regarding what the main concepts we had. So first of all, at the first lecture or the second lecture, we introduced perceptron. We introduced one node of our deep neural networks. And this node, what does it do? It takes the inputs, in this case 3 input variables, then multiply it on some weights, add bias, we never forget bias, and then apply some nonlinear function g, and we get an output. So if we write it mathematically, we will see this particular way to write it. So y, it's this nonlinear function of z, when that is sort of linear combination of x and w's, weights with and plus bias. And we saw these different functions that we can use as g. And can you name this function? What is this function? Okay, at least one of them. This is sigmoid. Come again? Sigmoid. Okay, this one? Yeah, this is ReLU. Okay, here you're correct. This is ReLU. So it's not leaky because it's 0 here. Leaky will have the slope, but this is not sigmoid actually. This is sigmoid. Sigmoid is between 0 and 1. This is tangent, tan h, and it goes from -1 to 1. So don't mix them. So yeah, but why do we need them? Why cannot we work without them? What's the reason to include nonlinear functions in our neural networks? Why we do that? Answer, because that's what I will ask you. Why do we need it? Why cannot we have just identity function somewhere here? So, okay, we just have this linear combination. Why we need to add nonlinearity? I will show you to the next. Okay, that's an answer, but I would like to ask. So if we have a linear functions and we put it into the multiple layers, doesn't really matter because linear combination of linear combinations is still linear combination. So we have no reason to actually grow our neural networks, and therefore we actually limited the prediction only linear relationships. And of course, that's not what we want because our relationships in general are quite non-linear. So that's why we need these functions. And this is already a little bit more deep neural network. We have an intermediate layer here. So we have input layer, output layer, and intermediate one, and we have a little bit more sophisticated computations. So now the main algorithm that you actually, I think, practice by yourself during the writing the code in the COM project or in a class can be represented like that. So first of all, of course, we define the problem. So whatever problem you have, you need to define it. Then what's important, you need to identify input and output of your problem. So what you have and what you want to predict. You need to decide then on architecture, because depending on your data, you have a different architecture. Then define train and test sets. That we will talk about a little bit later. Train your model. We also will talk about that. Evaluate your model. And hopefully enjoy a good model. So that's our sort of algorithm, our approach in general. So we will start with this particular step, identify input and output. So in here, let's work together a little bit, and I just would like to hear some examples, what we can use as input and what we can use as output, and for what particular problem we can do that. So any ideas what we can use for input? Just examples. Give me examples. What? Pictures, nice, yes. Pictures, we will say, let's say, two-dimensional arrays, yeah, because that's exactly how we usually represented two-dimensional plus a little bit of channels. Okay, so in this case, what you can have as output? Okay, so we have a picture-to-picture system. It's quite interesting. Examples. Can you give me an example why we need, in what particular task we can have that? Yeah, okay, yeah, that's autoencoder problem. It's in general, yes. In autoencoder, you have the same input and output. That's because you try to encode it and decode it again. This is a nice example. Can we have sort of some number? Okay, let's say a number from minus infinity to infinity. Example of the problem. Now, from minus infinity to infinity, it's not a classification problem. Just any real number. Okay, what can you find a problem that will require you to feed the picture into the neural network and get a number as output? And if it will be from the field of sort of mechanics or, I don't know, civil engineering, it will be really cool as well. Any example of the problem here? We feed a picture and I get number. Yeah, you can do that. Yes, you can say stress calculation, like in what would be the stress in the specific point if you just feed the image of your structure. Let's say that's what. Yes, stress prediction can work here. Like lifetime prediction as well. You look at again, I can create picture and see how long it will take. So lifetime. There is I don't know why it's doing that. Honestly, it's very annoying. So can I have from here integer numbers only? So let's say 0 or 1. So any problem that will look like that, you have a picture and get 0 or 1 at the end. Yeah, again, that's your home project too. It's exactly what you're doing there. I'll give you quite challenge. So we have a pictures here, and can we have from this one picture a video? So from one picture now you have the array of pictures, like time array. Can you see any application of that? Okay, animation, right? I wanted something from civil engineering or mechanics, but okay, animation, yes. You can do animation on, say, the stress field, for instance. That actually will be also animation as well. Animation, in this case, no, animation it should not go exactly here. Should we have a what was it? Yeah, exactly. So it will be a video. Let's say crack propagation or animation. And now I have a question. We put autoencoder here on the top. What should I put actually here on this arrow? What architecture should I use? GANs. Yeah, I think you can use GAN. I would say yes, I would agree with that. But something a little bit more simple. You see variation encoder because it's encoder at the end. It actually transfer picture to picture. GAN's sort of doing the same. It's not direct GAN. I would say GAN is kind of I can imagine how to use it, but I would not like to use GAN. Something simple. What? YOLO? Yeah, detect. YOLO will give you maybe either coordinates of this, but of this detection, or maybe sort of image with the squares there. In time, what architecture by definition works in time? Remember we talked about sequences. Like text, music, whatever. So here you can use recurrent neural network because technically speaking, each next frame depends on previous frames. So with a proper training, you can use RNN just to give RNN one image and predict what will happen in the next 10, let's say, time frame steps. So here I would say RNN is definitely something that at least should be mentioned. Okay, so I will, of course, not in this case, of course, as input, we can use some numbers. So for me, it was important that right now we have multiple different architectures that transfer one inputs to another, to outputs, and depending on what we want, we need to use different approaches. Nice to have it. So what do we need for machine learning model in general? So when you imagine you are trying to do your practice exercise, what usually we provide you, and what do you really need to start machine learning model and start training? What's important to have? That said, it's one of the main things, of course, and this is actually, I think, number one. Usually split into train, validation, and tests, dataset. And what else during the training you need to do with your model after each epoch, after each training? What are you actually doing there? Yes, you need to have the definition of loss function for a particular model. Without that, you cannot do anything. But technically speaking, that's two things that you need. You don't need a lot more. So data set and loss function. I will start with the data set. And my question is, why do we need to split our data set? Like, what's the purpose of that, splitting it to what we call here train, validation, and test? Why are we splitting that? Yep. We will see that in a couple of slides, but that's exactly the reason. Because we want our model to be trained on some data that it can operate with, but at the same time, we should have some sort of piece of data that is invisible for the model, and we do that. But I would like actually to, in this case, it's usually in many applications, you will see splitting only in train and test. Validation sometimes doesn't exist for that. So sometimes validation is mixed with a test, but from the pure kind of correctness, you really need to have the validation. Why? Because what's happening, you have your trained data set. Computer, your model, and you can see trained data set. And this data set that you are using actually during training, you see what's happening. Validation data set, it's a little bit more interesting because your model doesn't see validations data set, but you as a human see it. So where we are using, so if we just write it down, we have the train, and from the train data set, you get your weights of your model. That's exactly during the training process what's happening. You get your weights or filters, whatever. So that's what you get. What you get from validation data set? Can you guess? Model cannot see that, but you, as operator, can see the validation set. What, in this case, you get from the validation set? Come again? Loss you don't train as well. Yes, you get a loss. Absolutely right. So, but what in this case is the purpose of the test? No. Forget about reinforcement learning completely. Forget. Here we're just talking about it. Again, this is not, it's absolutely, I expected that you, because we usually do not stop on that, and maybe it was wrong, but in general, the idea is, I give you a question. How many layers, convolutional layers, should you have in your neural network? You don't know. You can try 3, you can try 4, you can try 5. Yes, and what would be the filter size and what would be the stride? That's something that you are checking on validation dataset. The validation dataset gives you so-called hyperparameters. It's something that you play with as a human, trying to make your model works. The model has no idea about validation data set, but you have an idea about that. So what you have here, it's so-called hyperparameters. Again, we will not go into these details, but it's something like layer size, number of layers. What you can also say here, learning rate. It's a hyperparameter. So because you can change learning rate and you see the validation data set will perform worse. So therefore, the purpose of validation data set is for you to find the optimal architecture for this specific task. Learning rate. And finally, the purpose of the test data set, when you as an operator found it, and say, this is ideal conditions. Now to check that everything is fair, you go to the test data set that you cannot change anymore. You cannot change right now. You cannot play on the test data set with the different learning rates. No, it's fixed. Everything is fixed on the validation data set. And then on the test data set, you just see how well your model performs. Again, that's why you see in many, many cases, test and validation are kind of mixed together because no one wants to do this correctly. So, and that's kind of normal already now. So final. And that's actually why when you do this training in our practice, you always see the validation loss. Not test data set loss, but it's even called validation loss. Because what we actually, at the end, what technically speaking we want, you just plug your test data set to the already trained model and give us confusion matrix, for instance. And that's because it's kind of, it will be a completely fair approach. But again, everyone is just right now more or less mixing this together. So good. That's why we split our data set. And do we always have data set? When we don't have it? Reinforcement learning. But again, we just skip it a bit. So it's a different, a very different field. To estimate how good our model is, which loss functions do we know? Can you name at least 2 of them? What? Binary cross entropy for classification problem, perfect. And for regression, what we are using usually? What? Who told? Yeah, mean square error. No, sparse and cross entropy is something that is for the classification with multiple classes. So be careful. So this is the 2 classical functions. One, this one for regression, and this one for classification. There is another function that you kind of, I expect you to at least remember the name, is this one. Do you remember how it's called? What it's called? Look at that and guess. Okay, the softmax. We used it for multiple for the classifications with the multiple labels, and what it gives us a vector. Let's say we have 4 classes, and it gives us probability of each class. So, for instance, something like 0.98, 0.01, 0.005, 0.005. So then we will look at the maximal argument and say, okay, so we take argmax, and we say we have a class 0. So that's another function that you need to be familiar with, and I think you used it a couple of times. Good. That's with the functions. So now the another step that we have is train your model. And I would like to give you a quite fundamental question. What does it mean? What does it mean to train the model? Mathematically, how you will... Oh, okay, not mathematically. How you will express that? Any ideas? Yeah, right. That's how you need to formulate it. Sort of, I don't expect you to write that, but the idea is to find the set of weights or set of the filters, like with the star in this case, that will give us the minimal value of loss function. Again, in this case, let me just write it that it's loss function. That's important to understand, and that's why I'm repeating that a little bit. Okay, that's what it means to train your model. Now the question, again, we had this in the lecture, how we are looking for such minimum. We have this problem. What we are using to look for this optimal solution? What algorithm? Exactly, we're using gradient descent. That's, again, that's how you write it, and we are looking for so this is a fundamental algorithm that we kind of should understand. And now my question is, this is the same gradient descent. How can we improve this approach? There are some tweaks that we can do, and we're actually doing that during the training, that helps us to converge faster and more reliably. Ideas? Learning rate we can change, yes. Alpha can change, but it's one actually of the approaches that will help a little bit. If you, let's say, decrease your learning rate gradually with training, that's quite a good answer. Change alpha. But more fundamentally, the problem here is if you look at that, this is a gradient operator. This operator and the loss function is calculated on whole data set. In this particular approach, we are really calculating this iteration on whole data set. What we can do in order to avoid that, and of course, calculations on whole data set are hard and also memory inefficient. If your computer is not super powerful, doesn't have a lot of RAM, you will have a problem. You will have the bottleneck here because you need to store enormous matrix there. But normalization kind of helps, but not because it sort of changes. The first thing that is important, and Atul mentioned that, is batches. So, and then you, of course, on the batch, you can do a normalization. If you remember what we did this so-called actually mini batch stochastic gradient descent. So what's happening here, we compute that for just some of the points. Remember when we have this model.fit, we have this batch size there. Remember, you say batch equal to 32. That's exactly what's happening. After each 32 points collected, we will update our weights. We are not waiting for a whole data set to be evaluated. We're doing that like that, and that helps quite a lot. And we can actually do it even more efficiently if we're all using this ADAM optimizer. It's adaptive moment estimator. Sort of the difference between this and just classical gradient descent, it takes into account previous steps. It calculates so-called moments, and it learns from it's adapt depending on the previous iterations. So again, mathematically we are not writing that, but it's important to know that when we do these optimizers, we technically speaking in TensorFlow, we can say our optimizer is SGD. So stochastic gradient descent. And if you try that, you will see that your model probably will converge as well, but it will be slower than if you use a little bit more advanced things like ADAM. That's important. And the question is what we should avoid during training. Do you remember that? I saw a lot of you don't remember that based on your practice exercises. But in general, what should we avoid? That imagine that we don't have this blue line right now. We have just data points, like this noisy data. And we would like to have something like that. Yes, that's right. That's what we're trying to hint. So we can have a situation when our model is not powerful. We will, let's say, do only linear model, or we have only one intermediate layer. In this case, what may happen, we may get this red line. There is still some correspondence to the data, but of course, it's not what we want. So that's what we call underfitting. There is alternative. It's overfitting. In overfitting, you see our perfect red curves goes through all points. But this model is useless because it works only on this particular data set. If we look at the test data set, of course, you understand we will not be able to fit it because it's just we're fitting the noise. And this is not something that we want to do. So in general, you can also express it in the terms of bias and variance. So you can treat bias. We have a high bias when you're underfitting. So your model is actually have a lot of shift. So if I will give it another, let's say, another set of points, it will also probably do something linear. So we have this high bias and low variance. Variance is a little bit harder to explain, but the idea of the variance is how sensitive your system to small changes in the training data set. So because if we say a trace data set and it will be a little bit different, you see your function will be completely different. So variance is sort of like resistance to the noise. We want to describe our data points quite accurately, but we don't want to describe the noise. So therefore, what we're aiming for usually during training is something that a low bias, low variance, but there is a fundamental theorem that's basically saying that it's impossible to have a zero bias and zero variance. You need to minimize them together. And I found a very nice illustration of that. There is actually even the factor that you can calculate. It's usually calculated as bias squared plus variance. And this is what happens. Here you have a model complexity on this axis, and you have this error. And if your model is extremely, extremely simple, you will have enormous bias because you cannot predict anything. But at the same time, it will be extremely robust over the variance. You can imagine I moved this point just a little bit. It will give me almost the same result. So this, if our model is not complex, if very simple, then the motion of these points will almost have no effect on our model. At the same time, we have enormous variance because we really cannot, enormous bias because we are quite far. Our function, if we calculate even mean square error, is very far from our points. So if our model gets extremely complex, then we can describe everything. Then we have this extremely precise red curve, and therefore, if we calculate bias, is technically speaking just a difference between predicted points and real points. You can treat it as mean square error. So we have zero mean square error almost here, but unfortunately, it's extremely sensitive to the small changes. So that's why variance here goes up, and therefore, if you calculate the total error, we have some optimal complexity of the model, and that's a trick. No one technically knows how to properly search for that. It's what we call hyperparameters. It's what when you play with different learning rates, with the different structures of the architectures of your models. Because what you want to do, you want to have the model that is still trainable and the model that can predict something, but at the same time do not overfit. So therefore, we need to have it in mind. And the question is how to absorb overfitting during training. Any ideas? Yeah, this is exactly how it looks if it's wrong. So you see the left column for the data set this is our loss function on the train, and this is a validation loss. You see what's happening here. We have extremely good convergence on our train data set. It's going down, it's going very, very close to zero. Unfortunately, what we see on the validation loss, it's actually increasing. Okay, there is some fluctuation, but we see it increases. So therefore, at the end, our model is perfect to fit our train data set, and this is very bad in fitting our validation data set. So this is example from here. It's very similar illustration from the TensorFlow, what will happen there. So be careful when you do that. Okay, now we had a small jump there. We discussed very briefly support vector machines. We didn't focus on that so much. We had some practice. But for me, it's important that you understand the purpose of the support vector machines. So, and I think that's a question. Usually here you have zeros and ones. You have usually have two different family of points. And do you remember what is the goal of support vector machine? What is the main goal? Yep. To find a line that separate them with some sort of in the best way. So let's formulate like that. There is of course a formula to describe what does it mean, but the goal of support vector machine is to find a line that will. Originally, if you have a linear kernel, it's a straight line. We also played a little bit, and you saw from the presentations from the previous classes that you can have the nonlinear kernels, and in this case you can separate some more complexly arranged data, so sort of circles or whatever. So, but in general, their goal is to find separating line linear or non-linear. And you see actually the SVMs here, they are not in deep learning. So they do not extract patterns from data. And yeah. There are some expansions of SVMs for the multiple classes, but we didn't even mention them. So it's possible, of course, you can expand it, but SVMs classically for the two classes, 0 and 1s. So, but yeah, technically speaking, you can do that. You can usually how it happens. You combine all classes except one into new class, and then separate this one class and all classes, and you find one border. Then you take another class, combine all remaining classes, another big class, and do that. So it's still step-by-step procedure. There is almost no tricks that allow to do it in parallel. Supervised or unsupervised? SVMs, how we classify them, supervised or unsupervised learning? Yeah, supervised because we have labels. Very simple. Supervised. Good. Oh, come on. So then we shifted to CNNs, convolutional neural networks. And actually, we started with the filters. And if you just a reminder what filter is, if you have, let's say, image 3 by 3, or actually more, it's infinite image, and you have, this is your image, and this is your filter, and you have 3 by 3 filter. We'll say with the values 1, 2, 3, 4, 5, 6, 7, 8, 9, and your image here has the values of, I don't know, let's do A, B, C, D, E, F, G, H, I, right? So when I say that I apply this filter for this image from like in this particular location, what should I have as expression? So if I do it, it's exactly what's called convolution. So I'm doing convolution or with this filter on the very large image, but now I'm just interested in this particular coordinate. So I apply this convolution to this coordinate. So what would I get? Exactly. Absolutely right. What I will get something like, yes, some of the corresponding things and so on. So that's what convolution is. So each pixel sort of getting replaced by surrounding. So, and we discussed two different filters. One of them is this one. Do you remember the name of the filter? See, we search for the boundaries. You apply some filter and you get very cool boundaries, in this case like that. No, it's called Canny Edge Detector, yeah, and in particular the filter is called Sobel filter. One of the components looks like that. It's for detection of the vertical edges. So there is another component. I just don't want to write it, and then you combine them as a square. So that's exactly the filter. And another filter, unfortunately, animation didn't work correctly. This one is of course called Gaussian blur. So what's happening in this case? There is a filter itself. It's 5 by 5 Gaussian blur. And in this case, what you are doing, let's say you're applying this filter for this point. What's happening? This point has a weight of 41, right? So you have, if you apply this, okay, let me just cut this thing here. If you apply this central part to this image, what you will get, instead of pixels that we have at some location like that, what we have we will replace its value by something like that: 16a plus 26b plus 16c plus 26d plus 41e plus 26f. Let me just finish it. Doesn't work like that. 26h plus 16i, and this value that we will calculate in the new image will replace 41. So that's sort of, and as you can see, it's more or less averaging of the surrounding pixel with the different weights. So we, of course, focus on the exact position of the pixel, but we add some information from the neighbors. And that's what we call filters, what we call convolutions, right? So, and based on that, we get absolutely amazing idea of convolutional layer. So again, what we can do, let's do the following. Right now, I'm switching the notation. I will say my image will have something like one. Okay, no, let's do not like that. Let's do, we are mathematicians, so we can live with a proper way to do that. So I have A1, A2, A3, A4, A5, 6, 7, 8, 9, 10. And I have filter F1, F2, F3, F4. And now I do operation of convolution. So, but I now look not only one on pixel, not looking at one pixel only. I'm looking in all possible sort of convolutions on this image. So, what does I have as an output? How many times can I apply this 3x3 filter on this particular 4x4 image? 4 times, yes. But what will be the dimensions in this case at the end? 2 times 2, exactly right. So what we will have something like that. And let's say that it will be B1, B2, B3, and B4. Just write equation for B1. It's killing me. What would be the expression for B1? Yeah, then then F4 in this case. F5 multiplied by, because they're a little bit different size. That's not very good numbering, because you probably would like to do it 1, 1 or something like that. But you kind of see, I will not write it down. So what's happening here, you just apply this filter here, and this thing will give you B1. If you then, let's say, apply the filter in this corner, it will give you B4. Again, super simple. That's operation, mathematical operation called convolution. And that's what we are using for convolutional neural networks. In convolutional neural networks, we have convolutional layers. And usually they're a little bit more sophisticated because we don't only have one sort of image, we have multiple channels in a row. So like that, this is the channels. And they convolve with the filters that also has the same amount of channels. So, and then you do the same, but you just also add everything between the channels. So you sort of add, you have two sums. Have a sum of the sum. You have some, again, I just don't want to write it. It was in the lectures, plus some biases actually there. And then you do not forget to apply a function. Nonlinear functions still need to be applied here. So my question is for you, considering we have this 8x8 with the 3 channels, and we have 2 filters, each of them 3x3x3, what would be the size of my output? Six by 6 is correct. I have a problem with 1. How many channels do we have after that? 6? No, 3. If we convolve this one with only top filter, we first of all convolve red, let's say red with the top yellow, then we green with the second yellow, and then blue with the bottom yellow, and we sum everything. We sum them together. No, we sum everything. Kind of, you do not, you have, let's say 1. I don't want to filter. Okay, 1, 2, 3. So what you actually have here, you will take red multiplied by 1 plus, again, 1. It's, again, this is not a number. It's how I describe the, maybe let's say D1, D2, D3 multiple. Even let's say I will do convolution D1 plus green with D2 plus blue with D3, and I sum them together, plus there's some bias. When I do red with the top layer, how many things do I have? What do I have as the dimensions if I have only red and only the top layer there? 6 by 6 by 1, right? Then, so this is a 6 by 6 by 1. Okay, this is so small. This one as well. This is as well. And actually it's something, I think in this case it's also the same. And now I sum them. I just sum, I do not just, they're summing. So what would be the answer from this one? What would be the total size? Exactly, 6 by 6 by 1. We sum everything. So we do not like it will be 6 by 6 by 1. But that's what I did only with these top things, with the thing there, only with this particular filter. I have second filter. I will do the same, and I will get here as well, 6 by 6 by 1. But then I do not add them together. I will stack them together. So I have 6 by 6 by 1, 6 by 6 by 1, and here I have a stack. So what? How many filters do I? What would the dimensions? Exactly. 6 by 6 by 2. So amount of the channels in the next stage depends on how many filters did you put there. Yeah. Yeah. It will be stacked. Yes, that's exactly. If you do it in TensorFlow in the practice, you will saw that how you define how many filters. Remember 16, 18, and then if you look at the dimensions of your the next layer, you will actually see that this number of filters transfers to the number of channels. So it's become a number of channels of the next one. So again, it was right now. I think it's very, very clear, right? I hope that's why I decided to repeat that, because usually with the numbering things, it's a little bit hard. So that's exactly what happens. That's perfect. That's what we want to remember. There are some modifications, of course. You probably remember the padding. So let's say if I have 3 by 3 filter, what would be expected output here? 2 by 2, we already did it, right? We will have image 2 by 2. So our image will shrink in size. So what we can do to avoid that? We can do a padding. So there is a way to to increase the size, and that's what you just need to remember. There is a way to do a padding, and there is a multiple actually approaches. You can just put zeros everywhere, or you can put averages. Doesn't really matter. What is right in this case? Right now, when we say that we go from 3 to 3 filter, you get 2x2 image. Stride is 1, right? Okay, let me do the following, because right now I cannot go, I cannot illustrate. Let's say we have a 2x2 filter. And stride 1. What would be my output? I have a filters 2x2 with a stride 1. What would be the dimensions of output? 3x3, absolutely fine. What if stride... let me do it green. If I will have stride 2, 2x2, because what we do, we'll do this 2, and then we jump twice. So we do not just move 1 pixel right, we just move 2 pixels right. So in this case, we have a 2x2. Oh yeah, that's exactly what you need to know about the strides. And finally, there is another layer. It's not for modification. It's max pooling or average pooling when you say that you have something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And what's happening, you transfer it to 2x2 output by just looking at the maximum values in the squares. So what would be the output in this case? What will be in this corner? Yes, 6, 8, 14, 16. That's max pooling. That's all. That's what you need to know about layers, more or less. Nice. And in general, so the trick to the successful CNN is to combine multiple convolution layers together with max pooling. You quite often just alternate them and then flatten things, add couple of, in this case, it's called under or flatten the previous parameter, and then you can have multiple dense layers. So the thing is, and I think you felt that in the practice, it's important because when you do unrolling or flattening, you lose all spatial information. Right now, you don't know which pixel is the neighbor of which pixel. So therefore, this transition loses all spatial. Wrong. So it's important to kind of do convolutions until the point when you're quite satisfied. Otherwise, again, why we do neural networks like that, convolutional neural networks, because we want to save amount of weights that we are training. Because in this case, you are not training weights, you are training the elements of the filters, and the filter is applied for whole image. Therefore, if you increase the size of the image, you kind of doesn't change the amount of unknown variables, because what's important, it's the filters. So therefore, never flatten it when you have still, let's see, go ahead. Yeah, okay. Just, but quickly. It's not that you do offset information. Of course, if you flatten, you can. Yeah. Okay. So what's happening is when you use, you could just take an image, and the first thing is you do is flatten, and then you do dense layers. The problem is that the dense layers, they look then, you have one neuron that's flattened. Well, if you flatten, you turn neurons with 1, 2, 3, so the pixels, 4. And these are basically then your connections for you get neurons. And this specific neuron is always connected to condition. So what it kind of does is this pixel y or left in the case of one number. So if you have a 0, the picture is 0, here is 0. With another picture with another 0, that's shifted. You have just look at this pixel here, and of course these are different pixels. In one case, it's black,
And in this case, the pixel is white here. So here it's black, here it's white. But both images still contain zero. So this is actually a bad thing, because you have images of the same class, but if you just look at the pixel value, they're different. So what we have from the evolution is, because we have the filter shift always over here. If the filter is here,
we just need to maybe
or
move a little bit to guys to see
sorry.
this way. Yes, that will be better.
Here, it doesn't matter, because you just look at patch here, right? So these patches are essentially the same. They don't depend on the position of the image. So you can learn these low-level features. And so, of course, in some point, you will have this part, and you will, due to the stacking of convolution layers, you will combine, of course, non-modular features until you get to the greater part. And that's usually when you have just maybe a 4x4 image, and this contains basically, is there a zero in the upper left corner, is there a zero in the upper right corner, is there zero, or something like that. So you have and then you can kind of flatten that, because you're just working with high-level features, and it doesn't matter that anymore that these high-level features, they don't need, you don't need to know at which position the image they are.
But that,
you just need to know that they're there.
Yes, but that's exactly what I kind of try to say, that you are losing spatial, like you don't really you don't care. Let's say if you try to detect a hole, you don't care where it's located. You just want to see it. So if you store all pixels, it will be absolutely inefficient. We talked about this storage of information, remember JPEG conversions and so on. It's a very similar sort of concept, just don't lose the spatial information. I think that's no, it's quite, I like it. It's a little bit. So again, you're just losing that. So no, thanks for the comment. This is a way maybe we need to think how to. So, but that idea, you can evolve it and look at this scheme, and actually look at what you did in your practice. Two things that you can observe while we are moving from the left to right. Two important things for all convolutional neural networks. Can you say something happening with the dimensions? What happens with the dimensions? Linear dimensions shrink. Your size of the image gets smaller and smaller. But if you look at the amount of channels, 3, 6, 16, it increases. So that's exactly how you sort of encode these high-level features there. So that's a very important aspect of CNNs. You shrink in the sort of linear dimensions, and in the third dimension, in plane directions, maybe linear is not correct exactly, a number of channels increases in output. So that's exactly the whole goal of these convolutions. Nice. So then what we talked a little bit about the YOLO. YOLO, it's just one of the models that can do detection and classification. So we do not only classify our images, but also detect when we have the object on the image. And my question for you would be, so before that, when we do a classification, what we used as the output, we used a class. We used 0 or 1, for instance. Yes, remember that? Or if we have multiple classes, we store 0, 1, or 2, or we use one hot vector. So our storage was like that. So let's say we have 3 classes. Right? So how we store it? We store it like that. 1, 0, 0. 0, 1, 0, and 0, 0, 1. This is called one-hot vectors. Question to you, how do we store our outputs here? When we train our model, we need to have some outputs. So what we have here? Do you remember? What is what's important things that we need to store if we want to do a detection and understand the positioning? What else beside of the class we need to store? It's quite obvious. Location, right. So what actually in this case we store, and if you remember, the vector looks like that. First, it's if their object. So let's say there isn't an object inside, so we need to put one. Because if there is no object, there is no reason to classify anything. So if there is no object, usually in literature you will see something like that. So 0 and then only question marks, because you have nothing. So but imagine that there is an object. So what you store in this case, you store I think it's a wrong you store the rectangle. So you have 1 bx, by, then you store height, then you store the width. Okay, let me just sweep it. And considering that we have 3 classes, so what we store as well? Our one hot vector. So you just plug this one hot vector here. And that's what you store in this case. Again, it's simplified version when we have only one object. So in this case, we know that it's object of the class number 3, and we know the coordinates and the size on the image. So that's a way how you store your outputs and you store your vectors in YOLO. And almost all these algorithms, because you bring your class and also you bring your position. Clear? Yes? If you have 3 classes, yeah. And if you do one class detection, usually if you have one class detection, you actually, if you just want to detect if there is a car, so you don't have this at all. So you have 1 and the coordinates, or 0 and nothing. Yes, for let's write it for the exclude kind of. That's just simplifying, because otherwise you just store nothing there as additional 1. Yes, okay. For multi-class, that's because when you need one hot vector in general, for one class, it's enough to say 1 yes, and then bx, by, bw, and bh. So yeah, so that will be enough. That will convey enough information. I mean, if you have a multiple, it's usually not. It's usually kind of you need to store this class. So, but this is absolutely right comment. Nice. So that's how we store it, and that's important things for YOLO. So in general, architecture of YOLO, of course, it's more sophisticated. It includes multiple backbone or head stuff, but in general, it's a convolutions, some sort of upsampling that we already did. There is some sort of max pooling here. So again, it's of course more and more advanced, and it's already the version number 8. So I don't know, it's super advanced. So what can we also do with images? We can do autoencoder, if you remember correctly. So autoencoder, it's a thing, and as Mara already mentioned, so we have input as an image and have output of the image. And what's the deal with autoencoder? Why? What makes them quite good for some specific tasks? What is the main feature? What is the main feature of autoencoder? Bottleneck. Yes, it condenses information and keep only the most important things. That's what you need to remember about autoencoder. The most let's say high, is it correct to say high level features? Yeah, probably. So, and therefore, you can use autoencoder for, let's say, for the coloring, for the denoising, and all the other stuff. You have the input and output the same dimensions, but you may have a different, let's say, in this case, color thing. So, supervised or unsupervised? This architecture goes under supervised or unsupervised umbrella. Unsupervised, exactly. That's correct. There is nothing you are doing here. It's like really, it's you don't have labels. You can have, of course, but by default you don't. And autoencoder architecture, that's how we use it first, can be used as anomaly detector. So we can actually train on one class and then see how well it performs on another class. Nice. So then we shifted. Right now, I just changed our lectures a little bit in terms of we didn't shift to generation afterward, but this is really close to the generation because autoencoder, what it does, it's sort of generating. So, and here we discussed 3 different architectures of the that enables the generation of new images, materials, or whatever. We looked through the literature to see how you can apply it for the mechanical problems, and one of them is variation and autoencoder. It's extremely similar to the autoencoder, except we have additional thing inside. I know that you are not very good in statistics, so you just need to see that what's important. It's not only compare the pixel-to-pixel values between images, but also to have this, if you look at whole data set, to have the same distribution inside. So therefore, you have 2 components of the loss function. One component is this one. It's when you really try to match the probabilities. And another one is this one, when you see how similar your images are. So it's, again, I understand that's probably a little bit harder than other topics because here you introduce these distances between probabilities. So, but the variational part is exactly about that. What you want, you would like to have this very nice, let's say, uniform distribution that will allow you to take whatever number you want, let's say between 0 and 1, and get the valid result. Without that, that's what you important, if I will ask you, without this part, central part, you cannot guarantee that all numbers from this latent space will give you a proper answer. Is it, Gerrit? Is it sort of the way how we can understand that? That's exactly what we want. So then there is another, a little bit different architecture called generative adversarial networks. And here it's easier to understand in general. So what's happening, you have a 2-player game in this case. You have a generator and a discriminator. So what's the role of the generator in GANs? Can you tell me what's the purpose of the generator? Generate what? Yeah, fake data, not noisy, but fake data. Take some noise, arbitrary number or vector, and generate something. What's the role of discriminator? Okay, and why this architecture works? Why this architecture does work during the training? Why we have during training have a better and better generation? Can you answer this? The goal of generator, right, is to generate something, but not just something random, but something that looks like what? No, it doesn't give a picture back. It gives sort of generator knows if the picture was detected as fake or not, right? No, look here, it doesn't works like it. So the idea again, let me in this case repeat example with the counterfeiting money. So the goal of generator is to generate something that looks extremely similar to the real money. So that's a goal of the generator. Goal of discriminator is not to be fooled. It's try to really detect the fake money, even they are getting closer to the real by the quality. So what's happening at the beginning? Generator produces some absolute random stuff, and discriminator, by looking at these images and looking at what generator provides, immediately start to say, this is fake, this is fake, this is fake. And generator, due to that, starts to get better and better because it actually penalizes the generator. So generator getting very sort of large value of loss function, and you want to minimize it. So generator starts to produce something a little bit more that looks like a little bit more real. So what's happening in this case, it can fool discriminator a couple of times. And then discriminator getting better and better, because right now he looks at the new data generated and learn maybe smaller features that will allow him to detect the fakery. And then they gradually they compete with each other and getting better and better. It's again, this is very similar, and I think this is exactly a very good example with the police and the mafia. So when criminals try to always create the money, they look as good as real, and police always getting better and better in detecting these fakes. So, and they're competing, and it's the same as when you have the defense and offense. They're competing against each other and getting better all the time. So, fake monies are better and better. Police are better and better. Yes, it has nothing.
I think the important part about the generator is that it's trying to generate something that is real, but for the generator, that means everything that gets past is criminal. So the mafia is not trying to produce money that looks exactly like that. It's just trying to produce money that's good enough.
Generator doesn't see real money. That's a little bit.
Just gets feedback. Was I caught or wasn't I caught? That's what it gets like.
So you can imagine that, let's say, that they're playing the game. If you call the number between, let's say, 10 and 12, then to 10 and 20, let's say, then discriminator will say that's real. So generator just randomly generate numbers like 1. Discriminator say fake. Then say 3, fake. And then you get generator generate 11. And the discriminator say real. So now generator may have already a concept that your number should be between 10 and 20. And then discriminator lower the bounds. Let's say, okay, now what I will consider real, because I see that it's getting faked more and more, like real numbers will be between 12, let's say, and 14. So it's getting so they're competing against each other. So that's exactly how it works. So, and of course, we also discussed the diffusion models a little bit. So it's a state-of-the-art thing when you have the noise and denoise step by step. So it's much larger and harder to train models, but they are very cool for specific applications. And this is a very important diagram, I think, is just show this compromise between the different aspects. So you see the generative adversarial networks, for instance, produce very high quality samples, and they're quite fast to sample. You just put a random number there and you get image. So that's exactly what we did, I think, in the last of the practices. We just put the number and get different images of the volcano, dog, whatever. So unfortunately, they are very, very hard to train because they have the mode collapse. For instance, you ask for the dog, it will always generate in the same dog. And you see from the architecture actually how it may happen. So let's say if your criminal learns to do one ideal bill, it will repeat it over and over again. So that's a little bit problem here. So we have variational autoencoders and very good fast sampling. So you fastly get from the noise image. You have a much better diversity, but usually the images are blurry. That's one of the things that you will see in the home project 3 if you do with variational encoders. And finally, this denoising diffusion models, really high quality, state of the art, generate whatever you want, computationally nightmarish for training and for generation as well, really, because you need to run through 50 iterations of neural network, and this is quite hard. So We also briefly discussed transfer learning. I think this concept you should really remember and should understand quite well. The idea here is when you train neural network and then you want to use it for something quite similar, it will be quite not smart to start from the scratch. You can reuse the knowledge. And can you give an example of the transfer learning? Any example? Anything, not necessarily from mechanics. Yep. Yes, you can add another class in your. Let's say YOLO right now that we used was trained on 100 classes only. So let's say you want to add a class, I don't know, of university building, and then you can really you already use pre-trained weights, and you save a lot of time for you. In general, transfer learning, you train your image, you train something on the images. Let's say rendered images. This is the same with what happened with the ants example, and then you really do real video images or something similar. So in general, how does it work? It's very simple. You have your already pre-trained neural network, and let's say you want to add something that sort of doesn't exist in this neural network. So what you are doing, because we remember these first layers can detect very simple features. Like remember edge detection. It's extremely simple feature. It's like clearly what's happening. So therefore, you will have edges on new data set and an old data set. So why discard that? Why discard, let's say we learn this Sobel filter, we learn this particular field or Gaussian blur. Why will discard that? It will be useful. So therefore, you keep everything here, just freeze these layers and just unfreeze something there. So allow weights during the training to change only in these last layers, and it's getting the work done in this case. So that's quite powerful example. You cannot train. You see this, I don't know, 41, 43, and then multiple zero parameters. You cannot train it all at home. And then we also briefly discussed at the last stage of this lesson about few-shot learning. So the idea that you, let's say, have a new class or you have a new thing and you don't want to retrain your neural network. And remember this, the goal here is not to predict the class, but just to say if this image and this image belong to the same class. So you compare like positive anchor image, the image that you're feeding, with a positive or negative image. Do you remember what the name of this architecture? It's called CMES networks, because what's happening here, the bottom and the top layers are absolutely identical. You just combine them into a loss function that looks a little bit different in comparison. So you can see it in the lecture, and that provides you with this thing that when you have a new object, you can really compare if it belongs to the already existing class or if it's a new class completely. And therefore, why it's called few-shot learning, because you do not relearn the model. Model is frozen. What you're actually doing, you just add things and compare what's happening there. Can you give me an example from, like, say, real life where this is extremely useful and exactly where it's applied all the time? Something architecture like that. When let's say you have a new object or subject and you need just a couple of images in order to then kind of to separate this from already existing samples. Any idea? Let's say that when you enter the office building, you have face detection. So what's important is just really compare your new image when you're just in the front of the door with your image there, and also to compare it with everyone else. So how algorithm works in this case, it's run around your face that you just take a picture of through this neural network already pre-trained, and what it gets at the end is so-called encoding. It's sort of the vector that will correspond to your face, and then it tries to look how far this vector from already existing vectors in a database. So yeah. Yes, it's similar. I would say it's kind of similar, but the loss functions here is different. So you can treat it as anomaly detection, for instance, like that. You've trained this neural network on 10 workers in your office, and then there is someone outside. Then his face will be encoded with already trained neural network. You get some vector, and then everyone will see that this vector is so far from the vectors of all existing guys, and therefore you will be rejected. It's very similar to anomaly detection from this point of view. You're absolutely right. It's more powerful, of course, because now, for instance, if you give this person access to your office, let's say this is your employer, you don't need to retrain anything. You don't. It will be automatically encoded. You say this is the encoding for this person after you run it through this neural network and get this, let's say, this value. And that would be enough. Now this person will arrive next time with a hat. Since the encoding is quite robust, usually during training, even the hat or maybe glasses will not affect it so much. That's the beauty of this approach. So, and that's why it's called, again, few-shot learning, because you don't need a lot of data to add a new class. And finally, at the end, what we start to talk about this sequential models, it's the whole idea that your next output can depend on the previous. So what you have here, and this is, again, it's important for us that you understand the idea that right now the samples doesn't just go inside of your prediction or classification. What's important is the sequence of the samples, and therefore you have these additional connectors. So if I remove these connectors, horizontal connectors, it will be just classical neural network. You put input, you get output. But here, your output or something that is calculated on input propagates through time on the right. So that's the main deal. And when we can apply them, I think at the beginning of this class, our lecture, I already mentioned that. Examples. Text generation, music, everything that signal processing, actually quite useful for that. And there are two, I remember it was really, I understand, hard to understand these two units, GRU and long-term LTSM. It's sorry, it's actually wrong. It's LSTM, a long short-term memory. I got confused a bit when I wrote it. Do you remember the idea of these things? Of course, I will not ask you to write me equation, what is like these gates inside, but what the idea, why, what the disadvantage of this particular approach is here on the top? What's the problem with this approach? Exactly. You have almost no direct connection. You of course, through these gradients, there is some small effect of the first on the third one, but it's much smaller than second on the third one. And if you go through 10 steps, you already forget what happened there. So this is why do we need them? For memory. And this is actually what's called memory line, for instance, in this particular case. So it allows you to get a much more complicated connections to the past or to the future. So, and finally, final lecture was, again, a new topic. It's sort of also sequential thinking, some sort of, but it's very different field of deep learning in general. It's deep reinforcement learning. And what components do we need to establish reinforcement learning problem? Do you remember? It's last lecture. So what's states? What else? State? Action? So, actions? Rewards. Yeah, technically speaking, you're kind of right. That's what we have. We have this agent. Of course, we need some agent. We need to have an environment. An agent will take some actions, get some update in the state, get some reward, and you repeat the cycle over and over again. So you have S as a space of states. You have actions, and it's sort of, they depend on the states. You can have different actions in the state. You have rewards, and if you combine them with this particular probability function that actually describes your chances to jump to another state, S prime, and get a reward R, depending on your current state S in A, you have so-called finite Markov decision process, and that's a very good thing to have because there are a lot of nice properties of the MDPs. Sorry. So remember that we can introduce. I think this is just basic fundamentals. Remember that we can introduce state value and action value functions. Remember, we just introduced something like that. So V pi, it depends only on the state. So it looks, let's say, on the square you're locating right now. Think about states as the positions in your labyrinth. Like this is a state. And action is where you can go, right up, right. So it depends on state, and it's just expectation of your total reward, total, how it's called? Return, if you stay in this state. So that's how much money at the end you will have. At the end. So kind of don't forget a little bit forget about this expectation, because since there is still we didn't discuss it, but in some cases there is a chance that you want to go to the state here, but probability functions say no, you will actually go to another state with another reward. So it's probabilistic in general, but we actually simplify it quite a lot, so you can forget about this expectation. But you don't forget about the letter pi. What is pi? Do you remember? What is pi? Pi, if you remember, and you should, it's called policy. It's your strategy of decision making. So your policy may be, I will take random actions. I randomly move right, left, left. This is your policy. And if you play by this policy, if you decided to play like that, you will get specific expectation at the end. You will get the specific reward at the end if you go that. What's idea in general is to make the best policy, optimal policy, because in many cases it's absolutely strange random policy when you just randomly pick. You get a better and better results if you start to act smart. So pi is sort of describe your smart strategy, and you try to improve it. And there is another way to introduce it. It's not only on the state, but also on an action. So what is my reward in the future if I will stay in this state, in the square, and move left, for instance? What will be my reward? And it, of course, also depends on the policy, because, again, I can be very random. And then idea here is very simple. You are trying to find the V's, and you try to find the pi's to get you the maximal reward at the end, the total reward. And that's what you need to know here. And why we introduce it, why we introduce these particular values, because it's very cool to work with them. We already had this example when we moved in the maze, and we update it all the time. And that's what actually happening in Q-learning. Whenever you make a decision and make a step, you see your result, and you update your Q value of your current state and action. So, for instance, if I go left and then go left again, and I just fall into abuse or whatever, something like that, I will not go there anymore, because I will say I will give my reward minus 100. Therefore, this reward will be transferred here. I will say minus 50, for instance, here, and then in the first stage I will have something minus 25. And now I will know that my reward, if I will go left, would be quite small. So therefore, I will not go there anymore. So that's exactly how it happens. So you just update your things, and there are two parameters that are important. It's like learning rate, like how good you're learning, that not go there. And also there is also discount factor, but we can ignore it a little bit for now. So that's the thing. That's a very iterative algorithm. And every time, when you have your Q table, that's important. Sort of what you have, you have this Q table. So here you have state and action, have the state and action, and between them you see how I would say not even like that. So you have let's say you going back, you can go only like that, and then in this case what you can have states, and you have go right and go left, and you can get value for all of these steps. So at the end you will get the values in each state, you know, left or right, how much it will give you. If approximately when you, on average, when you end the terminal state. That's what's important and what's happening here. And each time, on each step during training, you choose the maximum action with the maximum value. So if you say on the left -100 and on the right you have 1, you always go to the run. You always go to the right because there is a 1. Is it correct or we are missing something? In this statement that during training, all the time, you select the action with the highest value. Is it true? Remember what you did when you didn't do that, but remember one of the parameters that you played with during this car thingy? There was one parameter that tells why it's not true. When you need to know, at the beginning you start with zeros. You have no idea about your landscape. You have no idea where to move, how to move, where there is a, hole, where is a coin. You have no idea. And gradually, during training, you're actually going and updating this table. And I will say that it's imperative to every time go to the highest action. Why it would be incorrect? Because we need to balance between exploration and exploitation. That would be correct strategy when you already know everything. Of course, in this case, you do not risk and you do not go for unknown, because there will be no unknown if you properly explore the situation. So during training, remember this epsilon factor. Remember epsilon, that gives you a chance to take a random decision that maybe actually compromise you a lot. You may lose this particular episode, but there is a chance that there is a way that you haven't explored yet, and they will bring to, plus 100. So that's important. Then there is this epsilon parameter. Okay, nice. And then we actually, again, mentioned 2 ways to work with that. It's like classical way, when you have the action and state and action, you look at this Q table and update Q value, and there is a way to replace this Q table by the neural network when you predict the values like as a functions. But again, we didn't do any practice on that because it's really heavy computationally. Oh, and so we did the finished recap. So I will spend 5 more minutes, and I just typed the name of the course into the ChatGPT, like machine learning approaches and structural mechanics, and we have seen here that machine learning can be used in structural health monitoring. It's something that we did. Structural design optimization. I would say the home project 3, it's not about this maybe structural design optimization, but something that you can explore then. Material property estimations. That's what we did in home project 1. Remember, so you have a specific geometry or a specific, elasticity, strength, fatigue, life. So that's what we discussed. Failure prediction and risk assessment. Again, something that we already kind of try at least to cover. And in some literature, we saw that when we looked at the papers. Non-destructive testing. I'm not sure if we did it, but we did this thing when you look at the road cracks. Structural response prediction, again, very similar to home project 1, when you have some structure and you would like to predict response without doing a test, that you can do. This is something that we didn't cover. That was one of the plans to cover, but we decided not to. So you can simplify some models. And from the civil point of view, engineering point of view, sometimes you're really looking for the optimal position of their sensors, because you don't want to spend a lot of money on the sensors, but you want to get a lot of data. So you don't want to put the sensors next to each other because it will be redundant. So you would like to distribute them. So I know at least a couple of works that do with that. So this is a few examples. And again, this is very potentially interesting field to apply machine learning in all this civil engineering and mechanical engineering and whatever. So what's next? And this is a MIT technology review from the December last year. And what they promise, it's get ready for multi-purpose chatbots. And they say that GPT-4 may be able to handle more than just language. I'm actually not sure if it's right now. But for instance, BART, it's a Google Google model can take the images as inputs. You can upload the image into internet and then reference this image and ask to describe the image, and it will do that. So there is already quite close motion to this direction, and probably already better versions of these models when you can not only operate with the text but with the images. So AI's first red lines, new laws and hawkish regulators around the world want to put companies on the hook, and that's exactly what's happening everywhere, especially in Europe right now. Regulation here is a little bit strange, in my opinion, a little bit mental, but let's see. Big tech could lose its grip on fundamental AI research, and that's actually quite true. Right now, more and more small companies and even like open access models you can find in the internet. There is a multiple open access models of the language things that you can download. They are maybe not so powerful as ChatGPT, but very close. And big pharma is never going to be the same again. So right now, big revolution in the pharma with AI, with the discovery of new drugs based on AI methods. So it's really, really hot topic there. So but what I think, again, I'm not a very good predictor, but according to what I read, reinforcement learning will become more efficient and more widely spread. Reinforced learning is lagging behind deep learning in general. So I would say when deep learning was born in 2006, reinforcement learning gets quite a lot of recognition in 2014. So there is a 8-year gap, in my opinion, and therefore it will. And now reinforcement learning is actively implemented in the ChatGPT things. Like when you interact with ChatGPT learns from this interaction. So it's not stationary model anymore. It's really learn and implement the changes based on your inputs and outputs. And this is extremely important. And this is a fact. This is how you use reinforcement learning. Physics-informed neural networks look as a promising direction in field of physics, I would say. They're quite mathematically heavy, but they combine very big, very good things from neural networks, and also they utilize physics. So it helps you to have the advantage from the both fields. So you right now do not blindly predict something, you based it on the physics. And if you're interested in that, ETH Zurich 3 weeks ago published the whole course on the physically informed neural networks. And again, I will upload it. I will just upload the link on that in the email that I will send you in Ilias. Without AI, you will have worse chances in the job market. That's absolutely clear. So at least some basic AI understanding it's necessary. It's like right now, it's like programming and scripting on Python. No one asks you to be expert. No one asks you to finish your computer science degree with AI. But right now, it would be quite stupid not to go there in terms of not to at least have some idea about AI. Questions of sustainability will become more important. Actually, that's quite important aspect right now. There is a couple of papers that discuss carbon impact of artificial intelligence and ecological impact of high performance computing in general. Or it's right now it's getting quite heavy. I know actually also regulations from ETH Zurich. There is a couple of professors who refuse to run on a big cluster just because it's producing a lot of carbon. And questions of ethics will be important. So right now, 3 days ago or 4 days ago, the strike in the largest strike for the last 60 years of actors and writers in Hollywood. And one of the aspects is AI. Of course, you understand why the writers can be struggle with AI, because right now if ChatGPT can write a movie or whatever, what's the point of paying humans? And actors has a very similar problem, because right now the generative models become so powerful, so you can use the actor, record the actor, and then utilize his virtual basically replica for the movies without paying. So there is right now one of the big reasons why actors on the strike is actually AI. And of course, there is a classical question, and you can read about that in Wikipedia. It's a classical scenario. Do you familiar with this guy, by the way, Clippy? Have you who have seen this? I'm just curious. No, wait. Have you seen this thingy? Okay, that is just different generation. It's so fun. It actually was a sort of how you call it, helper in the Microsoft Word. It's like it just give you advices how to print it. And again, if you are from like young generation, you probably have no idea who this guy is. It's a very annoying guy called Clippy. But the idea, this is a hypothetical scenario of paperclip maximizer. I think it's proposed by the one professor from Cambridge, right? Or from some sort of big university. And the idea, imagine your AI has a goal of producing the paperclips and maximize the production of the paperclips. And if you will not incorporate the ethics inside of this robot will destroy whole humanity, will destroy all Earth, just to fulfill the goal of maximizing the production of the paperclip. So that's another scenario that needs to be considered in general. So, however, in this case, if you remember the first lecture, that's our prediction from 1958. Within 10 years, a digital computer will be the world's chess champion. Didn't happen, happened only 40 years later. Machines will be capable within 20 years of doing any work a man can do. Still didn't happen. Within a generation, the problem of creating artificial intelligence will be substantially solved. No. And from this to 8 years, we will have a machine with the general intelligence of average human being. 50 years, like, nah, nothing like that. So all predictions are quite random. So what's next? Definitely, it's an exam. I see it. I like it. And we really would like to thank you a lot for your interest towards our class. It was really important. I really liked teaching for you. So thanks a lot.